morning, everyone. My name is Shengye from the University of Manchester, and I'm delighted to have the opportunity to give a presentation on my current work. And my topic is the data needs for load forecasting at different aggregation levels using LSTM networks. And the main contribution of this work is that it proposes an hourly short-term load forecasting for using long short-term memory neural networks for 3 aggregation levels using the Gaussian precise-based hyperparameter tuning method and external factors. And at the start, the load forecasting can provide an insight of the future power consumption needs at different aggregation levels. Also, we can use this to help us to keep the balance between the power supply and demand. And with precise load forecasting results, we can, for example, the electric utilities can make some economic investment decisions. The distribution system operators can also optimize the power dispatching process. And for the end users, they can also save their electricity bills by changing consumption patterns. And the current works about the load forecasting can mainly be categorized into the traditional methods as well as the AI-based method. And in this work, a novel deep learning neural network based on the long short-term memory is adopted, since it's more applicable for processing the nonlinear data set as well as extracting features automatically. And so the first step is for the load forecasting is about the data preparation. And here we have selected the 3 types historical year-long data sets from the Dayton City as well as the Western Massachusetts in United States to represent 3 aggregation levels. And in addition, the external factors, including the temperature, humidity, as well as the wind speed, is also considered in this study. So, and the next step is to investigate the Spearman correlation coefficients between the load data as well as the external factors. Although the value of coefficients varies in different seasons, but they all indicate that the external factors will impact the power consumption to some extent. So, also considering that the load data with previous time steps tend to improve the load forecasting to some extent, there are 5 input combinations are created as the input to the LSTM model. And they are shown in this table to investigate the influence of the external factors on the load forecasting performance. Next, we'll go to the hyperparameter tuning procedure, and we can see the hyperparameter tuning. They can help us to determine an optimal model. As well, we can also improve the load prediction accuracy using this method. And the hyperparameters of LSTM model mainly include the number of hidden layers, number of neurons, activation function, optimizer, epochs, batch size, as well as the loopback time steps. And the working flow of the Gaussian precise-based method can be described using this chart on the left. The first step is to determine the hyperparameter searching space, and next we can create the model using the potential hyperparameters in the given searching space, and then we can feed the training and testing data set to the model and calculate the error matrix and searching for the minimum one, which can represent the optimal model. And finally, we need to repeat the Gaussian process for maybe 80 times to get more precise results. And once the LSTM model is optimally tuned, we can use the validation data set to obtain the result of different aggregation levels. At first, we can see at the city level, the input data set combinations, including the load data with loopback time steps and external factors, is selected as the optimal one. And its CV value, namely the coefficient of variation, is equal to 0.016. And it can also be obtained from this plot that at the city level, the predicted curve matches well with the actual value, indicating a satisfactory load forecasting performance. And also, at the substation level, the input tabs, including the load data with loopback timestamps and the temperature data with loopback timestamps, is considered as our optimal one. And we see CV value is equal to 0.076. It can also be observed from the plot that in this case, the LSTM model also showed good predicting accuracy. Finally, at the household level, the load data with loopback timestamps and temperature only is selected, although its CV value can reach about 0.413. And we can see that in this case, the LSTM model cannot deal well with the peak values as it underestimating them, which can be attributed to the high volatility existing in the household level dataset. And after that, I have compared the 3 CDF plots in different aggregation levels and considering all 5 input tabs. We can observe from this figure that the 90th percentile relative error can range from about 2.6% to 11.9%, and finally to 62.3% at different aggregation levels, following the same LSTM forecasting framework, which means that the forecasting accuracy will decrease with the reduction of aggregation level. So finally, here are the conclusions I can summarize from this study. The first, the higher aggregation level, they require more comprehensive external data for reliable load forecasting, and they also benefit from the loopback timestamps. However, the external factors, its influence will reduce at lower aggregation level. And second, the forecasting accuracy will decrease with the reduction of aggregation level, but the training time will increase in the same time. Finally, the household level forecasting, they may require some more complex LSTM model structure, for example, the higher number of hidden layers for better forecasting performance. And there is so much for today. Thanks for your attention. I'll be glad to answer any questions you might have.
Okay, thank you for your presentation. So, any questions from the audience? Okay, all right.
I will ask one as Shengye PhD supervisor at Jelena, Ponocko, University of Manchester. Thank you, Shengye. So my question is, who would benefit from this methodology, and why did you look into different combinations of input data for load forecasting and how that can affect load forecasting accuracy?
All right, thank you for your question. And in this research, I have considered the external factors, including temperature, humidity, as well as the wind speed and the day type. For example, the working day or non-working day. They are all considered in this study. And I think since at first I have investigated the experimental correlation coefficients between the load data and the external factors to see if the power consumption will be affected by the factors. And I found they all have a strong correlation with each other, although it varies in different seasons. And I believe that at higher aggregation levels and they will more benefit from these vital factors, but at lower aggregation levels, they only need the load data as well as the temperature data to realize more reliable load forecasting performance. And as for who will be benefit from this study, I believe the first is about the electricity utilities, since they can make a investment decision, for example, like the amount of power they need to purchase ahead and to meet the demand in the next day or in the next time period. And next should be the distribution system operators, and they can optimize the dispatching process, and if at the household level, if the resident is clear about how much amount of power they will consume in the next time period, they can also depend on different electricity price to make their consumption patterns. Yeah, so that's all.
Okay, thank you.